Hi everyone. I think we are live. You can let me know if you can hear me. Okay. So let's start. Uh, yeah, this was the question asked today. So it says that we have been given an array of strings. So basically a vector of strings. So you have so many strings, and further it says that it is containing n unique binary strings, each of length n. So all of us understand what's a binary string, right? In binary string, a character could either be 0 or it could be 1. The important thing is that in this collection, every item is unique. So um, let's say the size of this is 3. Okay, that means I'm going to have 3 unique strings. Okay, furthermore, each string that I have is going to be of the same length n. Okay, so if the size of this is 3, the size of each string is also going to be 3. So for instance, let's say you have this, and that. So you can see that all of them are unique and all of them are of length 3, which is also the length of your array, correct? Now uh, what we have to do is that we have to return a binary string of length n that does not appear in this array. So we can think of so many strings, so many binary strings which are of length 3 and are not present in this array. For example, I can just have 0, 0, 0. I can also have 1, 1, 1. So if you look at 0, 0, 0, is it present? No. If you look at this, is it present? No. If you look at anything else, let's say 0, 1, 1, is it present? No. So any of these can be returned by you. Now it also goes on to say that if there are multiple answers, like we had multiple answers here in this case we can return any of them. So it doesn't force me to return a specific answer. So it looks like a very weird question, to be honest, and I think weird as well as easy. But you know, the weirdness is there because if you look at the constraint which says that the size of each string is equal to the size of array, this has something to do with a really innovative solution. So I'll talk about that in some time. But what is the brute force approach that you can think of for this question? So if somebody has to think in a very, very fundamental manner, what we can do is that, hey, every binary string represents a particular integer, right? For example, this represents 2. This represents 6, I think, yeah. And this represents 1, right? So what we can do is we can probably store all these things somewhere. So let's say they have been stored somewhere, 2, 6, 1. And all that we have to do is we have to return any value like 3 or 4 or 7 or anything like that. So once we have converted these string into their corresponding integer values, we can go ahead and store them somewhere. And after that, what we can do is, after that we can just check. We can check that what all numbers could be represented by a bit string of size 3. So tell me, like, how many distinct numbers can be represented by a bit string of size 3? So you can represent 0, 0, 0, you can represent 0, 0, 1, you can represent 0, 1, 0, then 0, 1, 1, which is 3, then you can represent this, which is 4, and then you can represent 5. You can also represent 6, and then finally you can represent 7. So this is the smallest that we can get. The smallest that we can get is obviously 0 when all the bits are 0 each. And the largest that we could get here was 7. And when did we get 7? We got 7 when we made every bit as 1, 1, 1. Now you can generalize it. you can generalize it in this manner that, hey, here the number of bits was 3. So all the numbers from 0 to 2 power 3 minus 1 could be well generated. So it means that if the size is n and we are considering bit strings of size n, then all the bit strings, then all the numbers, all the integers from 0 to 2 power n minus 1 can be represented. So what I can do is I can simply run a loop. I can simply run a loop over this range, and whenever I get a number in this range, let's call that number as I, we can check whether that number I is present in this collection or not. If it is not present, it is guaranteed that that can be our answer. As simple as that. For example, in this case, you would have iterated from 0 to 7. Now, in the first iteration itself, you would have seen that 0 is not present here. If it is not present here, that certainly means that whatever is the binary representation of 0, that can be our answer. So this is the simplest solution that we can have. Also looking at it, if you look at the constraints, just look at how small the constraints are. The value of n is not greater than 16, right? Didn't get the last part. Can you please repeat? Yeah, super simple. You understood it, that how we created this collection of integers that are represented by these different strings, right? We didn't have to do much. We simply had to convert these strings into integers, and then we simply stored those integers inside a collection inside somewhere, right? And now I believe you also got this part where we discussed that if the size of your bit string is n, then the maximum number that you can represent is 2 power n minus 1. So we can simply iterate on all the numbers from 0 to 2 power n minus 1, and we can check whether that number is present inside it or not. Either it will be present or it will not be present, right? These are the only possibilities. Now if it is not present, that means that is a missing number, and its binary representation will be of size n, so we can simply return that. We can return the binary representation of it. Now you know here n is very small, it is 16 because it is 16. Now 2 power 16, how much it is? It's not very big, I assume. So the number of iterations that would happen would also be very small, and to be honest, these many iterations would not happen because the size of your array is equal to n, right? So the size of array will be not more than 16. So the number of iterations that you will have will also not be more than 16. Because just think about it, in the worst case what can happen is that I equals to 0 was present, I equals to 1 was present, I equals to 2 was present, 3, 4, 5, 6 till 15 was present. So if everything from 0 to 15 was present, that means the next thing that I am going to get will not be present, because the size is that much only. So the number of iterations that I am going to have is not going to be very humongous. It's going to be very small. Does this point make sense? How many of you understand this basic solution here? Right? Okay. So there was nothing special about it. If you have to talk about the, let's say, time complexity, then I would say time complexity depends upon where you are storing these numbers. So usually tell me which data structure comes to your mind if you have to store these numbers. I'm sure those of you who have studied about hashing, you might feel that let's go ahead and use the idea of hashing. Let's store them inside a hash map. So yeah, if you store them inside hash map, it will be very easy for you to check whether I, whatever the value of I is, it is present or not, right? So hash map is an ideal data structure. Now if you talk about the time complexity, the first thing that we are doing is we are simply iterating on this thing, on this array, and then what we are doing is we are converting every string into its decimal equivalent, and then we are pushing that into the hash map. So the steps are something like this. We are going to iterate over nums, and now for each num we are converting it into its decimal equivalent. So if you look at it, how many iterations will be there? The number of iterations will be equal to the size of nums, which is n. So we are going to have n iterations here. Now for each number, when you convert it, how much will that conversion process take? So if you have to convert, let's say this, that means you have to iterate all the characters of it, right? So you see that this particular character is 1, so you will add 1 into 2 power 1 to the answer. So each call to this convert method is going to take n more time. So this is going to take n square amount of time in order to create this hash map. Once this hash map has been created, then we know that this particular part is not going to take a lot of time. This will just last for, you know, n more iterations, because the number of elements that we have is also order of n. So for each element we can do an order 1 lookup in the hash map. You know, amortized complexity of lookups in hash map is order 1, and you can get the number which is not present, and then finally you can convert that number into its decimal equivalent, binary equivalent, and return that. This is the step which is going to consume the most amount of time. So this is going to be n square algorithm. Yeah, there is some extra space also that we are using because we are storing all of them inside a hash map, and that hash map could be of size order n. In fact, it will be of size order n because every element is unique, correct? Okay. Now, can we do something better? Can we come up with a better approach for this? So one of you, Rachit, is saying, can we try digit by digit match from the end? Digit by digit. When you say that, whose digit with whose digit? Do you want to compare the digits of all the items that are there inside this nums? Just think about it. In the meantime, I would talk about the most interesting part of this question. In fact, the most interesting solution. I also, honestly speaking, got to learn about it today, and it appeared to me as a very simple but very beautiful thing at the same time. So let's say there are two strings, S1, okay, and S2. Both of them are of same length. Let's say the length is n, correct? Now, how much is enough? How much is enough to ensure that both the strings are different? Tell me. It's enough, yes, to have difference at just one place. What I mean by that is, let's say it is 0, it's 1 0 1 1 0 1, something like this. Now if you want S2 to be different than S1, then just change any one place. So let's say at this place you have 1, then make this place to have 0. That's it. So even if at one place there is difference, I can say that both the strings are different, correct? Now think of it in this manner. Let's say you have been given two strings, two simple strings of size 2. The first one is 0 1 and the second one is 1 1, and you have to solve this question. So you can see that you have two strings, both of them are of size 2. Now I want to generate a new string. So can I do something like this, that hey, the new string that I am going to generate, it should be different from this. So let me make it different from this at this particular character. So let me make it different from this at this particular character, which is at index number 0, correct? So if here I have a 0, at the index 0, I would want to have 1, correct? Now let's move on to the next index, and let's move on to the next index for the next string. So your next string is this, and the next index is this 1. Now because I have a 1 here, let me have a 0. So did you see what happened? We germinated a string which is different, I'll write it, which is different from my first string at index 0 and it is different from my second string at index 1. Do you look at it? This is different from my first string at index 1 because at index 0, because at index 0 you have 0 here and here you have 1, and it is different from the next string at this index 1 because at index 1 you have 1 here, you have 0. So it means that it is different from both the strings. And if it is different from both the strings, that means this is what our answer is. You know, you can look at any other example. Let's say you have been given 3 strings of size 3. This, that, and that. Okay. Now I am going to follow the same rule. I want to create a new string and I want it to differ from all the strings at a specific position, at a specific index. So like here, if I look at the first string, at the index 0 there is 1. So I would make sure that it starts with 0 so that no matter what I create, it is definitely different from this. Now I'll move on to the next string, and in the next string I'll look at the next index. So at the next index I have a 1 here, so I would want to place a 0, and that will ensure that this is going to be different from that. Now I'll move on to the next, and here I'll see I have a 0. Okay, and because I have a 0, I would want to have a 1 here. Now do you see what we ended up creating is different than the first, second as well as third string? Does that make sense? How many of you understand this idea? Right? Simple enough to comprehend, isn't it? Now if you look at it here, what I have been doing is that I have isn't it a beautiful approach? It is a beautiful approach, right? This is a heuristic approach. What do you mean by that? Do you mean that when you talk about heuristic approach, you also have to look at the kind of constraints that you have? Here the constraint says that you have n strings of size n. Okay, so do you think it will give you a wrong answer in certain case for that particular constraint? I mean, if no, then it's just a normal approach, isn't it? Anyways, yeah. Here, what was the most important thing for me? The most important thing for me was to ensure that the string that I am creating, if I refer to that by name S, it should differ by at least one character from all other strings. So, you know, it was totally up to me. If I would have wanted, I would have said that, hey, you know, the string that I'm going to create is going to have, 3 places inside it: the first character, second character, and third character. So what I'll do is, I'll make my string differ from the first string at index 1. So here at index 1 I have got a 1. Instead, let me have a 0 here, right? Okay, now index 1 is done here. Okay, here I would say I would make it different at index 0. Here at index 0 I have a 0, so I would make it have a 1. And I would make it different from the next string at this character. Here I have a 0, so here I would have a 1. So did you see whatever ended up getting created is different than all 3 of them? So the point is, if you choose index I here, you can choose some other index j here, and then you choose some other index k here, right? Here what I did to make things simple, I started choosing index 0, index 1, index 2. So basically I started choosing indices in a diagonal manner just to keep things simple for me. But if you would have wanted, you could also have gone in this way. You could also have considered this to first decide your, the last character, this to decide your second last character, and then this to decide your first character. This statement is such a common sense, isn't it? And this is what we have made use of. Just ensure one thing, that do not use the same index for multiple strings, because if you do anything like that, let's say you see that you have a 0 here and you change it back to 1, right? And then you see that you have a 1 here and then you change it back to 0. I mean that does not make sense. In that case, you are neither generating this string nor keeping a certain character fixed. So the important thing is to, you know, pick different characters in different strings and then ensure that whatever you end up getting is your answer. Now, few things. In the beginning of the class, I told you that why do we have such a kind of constraint that the size of each string is equal to the size of a vector. But now a lot of you would have automatically understood that why we have such constraint. Did you? How many of you could understand that on your own? Let's say you had this as your input. So you have 3 strings of size 2. Now, let's say you want to create your answer. So you see that you have a 0 here, so you put a 1. In this string, you see you have a 0 here, you put a 1. What you got is not different. It is one of these 3. So this approach is going to work only if the number of strings is equal to the number of characters that you have. Is it absolutely clear to everyone that why this approach works, and most importantly when this approach works? Yeah. So if I have to go by this approach, what I can do is I can create a string answer, which is to start with empty, and then I have to traverse diagonally in this, right? So I can just iterate from 0 and I can go all the way till nums dot size -1, and here I can have a logic. So if you are in ith string, you are looking at the ith character. Remember, you are moving diagonally, right? And now what I can do is I can create a temporary string for now, which is, let's say, empty. And now if I see that I don't even need this, I'll simply write if nums of I is equals to 0. If this is equals to 0, then I am going to do answer plus equals to 1. Else I am going to do answer plus equals to 0. That's it. And then finally I can return my answer. Let's run and see if we are lucky. It works. You can run on more test cases. And then you can submit. Okay, so it works, right? And this has the best complexity also, and I believe you guys can understand why that's the case. What will be the complexity? So as you can see here, first of all, we are not using any extra space. In the last question we had to create an extra hash map. So do you see any extra space being used here? No. Now this loop is going to run for n times, and whenever it runs we are doing string concatenation. Now see, when you are doing string concatenation using this operator, and that too, the complexity of this will depend upon your language. So if you have Java, and in Java you are doing brute force concatenation of string, then because strings are immutable, it will have a linear cost every time. So your complexity will be n square. So in languages like Java, I would recommend you to use something like a string buffer. Okay, but in language like C++, if you use this operator, then the behavior is very much like appending at the end of a vector, right? So in this case, the appending of one character at a time will not incur cost of order n time each iteration. So the amortized complexity of that will be order 1 only in each step. So it will be back to order n. So yeah, doesn't matter which language you are using, you have to use the right construct there. If you are using Java or something like that, please use your string buffer or any other replacement, whatever you like. Here you are good with this operator. Okay, Cool. So that was all about it. I hope it was clear. It was an easy but a good question which taught us a very beautiful trick which hopefully we can use in some tricky questions of bit manipulation in future if we at all get that right. Great, then let's meet again tomorrow and continue solving. Okay, bye everyone, good night.